Hello, everyone. Today I'm going to be presenting or showing you a presentation that we just recently did in the ACA, American Crystallographic Association meeting this year in July. I'm happy that you are watching this. If you are watching this, it's because you are interested in electron diffraction and probably in our electron diffractometer, the ELDICO ED-1. So today I'm just gonna try to give you an overview of the capabilities and differences that this electron diffractometer has compared to other systems that can do also electron diffraction. My name is Gustavo Santiso-Quinones. I'm one of the founders of ELDICO Scientific, and I'm a senior scientist here, and I'm also responsible for the commercialization of this device. So let's start. In the agenda that I'm going to be speaking today, I'm going to be talking about briefly of electron diffraction and bottleneck, which was always instrumentation. I will show you that there's a dedicated device for ED experiment purposes. Now, many have asked, why is this device horizontal and it's not vertical like a microscope? Well, I will show you why. It has some physical features or physical properties, why it's horizontal, but also it's a very interesting thing related to the data collection. Last but not least, I'm going to show you about the other parts of the dedicated device, the source, the goniometer, the drift tube, and automation, which is something that we are running right now at the present time to be able to get 24/7 high throughput. So with that, let me start the story. In 2014, me and my business partner, Gunther Steinfeld, we founded a company which is called Crystallize. Now, our experience in crystallization and single crystal X-ray diffraction were used in this company. And within that journey with working with the pharmaceutical industry, we came across a publication on electron diffraction. Now, we were interested because of the potential of this, and we tried some experiments in 2017 and 2018 where we were aiming for organic molecules and tried to determine the structure directly from a pill. Now, this was published in collaboration with Tim Grune and many others. The paper is called Rapid Structure Determination of Macrocrystalline Molecular Compounds Using Electron Diffraction. Now, interestingly, this paper and one more paper from the United States were nominated at the same time by Science for Breakthrough of the Year due to the potential that was basically done with or described within these papers. So at that time, our mission was to have an electron diffractometer, which could be accessible for anyone. And that's the foundation of ELDICO Scientific. Now, within this vision, the whole idea is to have a system that can use or uses continuous rotation for generating diffraction series, requires no knowledge on TM or microscopy, has been optimized for diffraction experiments, has been optimized for organic molecules, has been optimized for sensitive materials, and it's capable to adapt to new applications in the solid state characterization field. Last but not least, it has to have a comparable process or workflow for single crystal X-ray diffraction, because this is what all of us crystallographers are used to and have been using for the past 60, 70 years. So with this slide, I'm showing you here the workflow of a single crystal X-ray diffraction in electron diffraction. And as you can see, they are one-to-one comparable. Of course, within the different experimental parts that need to be adequated or trimmed to the purpose. Now, interestingly is that the structure at the end, or you can use a crystallographic software like you have been using in X-ray diffraction. And this basically goes the same one-to-one. Of course, you can always do extra work, the so-called dynamical refinement, where you would require some extra efforts. But at the end of the day, you can see that the workflow is exactly the same from all the way to sample prepare or having a sample and getting a solution. Now, within X-ray crystallography, the bottleneck is always the crystal size, because you need to grow crystals to a certain size so that you can use it in your in-house device or even in a synchrotron facility. So we are talking about the micrometer range. Now, with electron diffraction, we can analyze crystals in the nanometer range. But the bottleneck of electron diffraction was until 2021, the instrumentation, because you needed to do some adaptations to a microscope. And now this has been solved by having dedicated system in the market. So this is a dedicated electron diffractometer, the ELDICO ED-1. It's easy to use, requires no knowledge on TEM or microscopy, has been optimized for organic molecules, has more space in the vicinity of the sample, which allows us for a higher rotation angle and also enhances the capabilities for new applications. Has better diffraction data quality compared to microscopes. We don't need to do any correction on our raw data because we don't have any lenses after the sample. I'll come more into detail later. And it's easy to use even under cryo conditions for sensitive materials. Last but not least, because of its design and because of the way it was constructed, automation, it's easier to implement compared to any other available system on the market. So this device makes the structural elucidation process faster, makes the process of substance identification faster, and uses very little amounts of material, so you're at the end saving cost and manpower efforts. So let's go into the horizontal thing. So here's the device which has been installed at one of our customers. As you can see, it is horizontal. Now there are many reasons for that. First, the weight distribution is on a larger area. So therefore, we don't need any special floor. We can put it in the first floor or in the 10th floor or in the basement. You don't need any special ceiling height also. So you don't require special rooms for your high TEM or electron diffractometer TEM based because it's horizontal. And last but not least, it's about the rotation. So the precision of our goniometer on this horizontal system. Now let me try to show you that with the schematic diagram here. So if our system is horizontal, our beam is horizontal, and our rotation axis is basically parallel to the gravity. While in microscopes, your rotation axis is perpendicular to the gravity. So this, of course, within the length induces a sphere of confusion in your crystals, and therefore your rotation, it's not that nice. Your crystals are going out, so you either need to track for your crystals or you need to compensate for that. Now here's the heart of our device. This is how our device looks like. Now, if you've been doing single crystal X-ray diffraction, you would see very, very good similarities. So you have a source. Then and in this case, because we use electrons, we need to have some kind of lenses or deflectors. We have an octagon here where our sample is placed. So this is the area where you have your sample. In this case, because we work in vacuum, electrons need to work in vacuum. We have some kind of chamber, which also can be used for transferring cold samples. We have our goniometer, basically which is enhanced for or made precise for a continuous rotation. And last but not least, we have our detector. Now I'm going to talk into details of this in the next slides. So our beam has been optimized. Our supplier is Exilon, the supplier of the metal jet used in X-ray crystallography for many years. It's our trusted partner. We use an LAB6 source, which is operated at 160 kilo electron volts, and it has been optimized for the purpose of electron diffraction. We have two types of beams. We have the so-called STEM beam, which we are used for imaging to identify our particles, and we have a very, very parallel diffraction beam. Now, some people have used our data exactly to test on the parallelicity of the diffraction beam, and they have told us that our beam is one of the most parallel beams or the most parallel beam that they have seen in the field of electron diffraction. So what other features do we have in this device compared to a microscope? Well, while we're searching for particles, most of the time in a microscope, you would be using TEM mode. We use the STEM mode. What does that mean? That means that you're illuminating already all your particles before even you have started your electron diffraction experiment. And therefore, particles which are beam sensitive would just die faster in your experiment. So we have a very small beam, and the amount of flux density is also optimized so that we can even treat organic materials at room temperature. No. Our diffraction beam has a fixed position, so it's not moving. We are not doing any tracking of the particles, or we are not moving our beam, and therefore our data is less prone to errors. We don't need to do corrections in our data. Last but not least, cryo measurements are not mandatory, rather necessary for the purpose of cryo options, because many of the materials which are beam sensitive on a microscope can still be measured on our device at room temperature. Another important feature of our STEM mode is the sharpness of your image at high degree. So in this case, if you compare here at 50 degrees of rotation, we can still see and recognize the particles. This has been designed for our purposes, and we are the only ones who could that at the present time. Now let's go into the goniometer, the motors, which is very unique for electron diffraction. Because of the amount of motors X, Y, Z, and rotator motor that we have, we can align basically any particle on the grid. We can rotate around any particle precise. Moreover, we can do fast continuous rotation for low dose experiments. We have a higher degree of rotation than others. Our rotation accuracy and stability is reflected in the data quality, and by contact cooling, we can do low temperature measurements. Our goniometer is very precise, and this is part of the new things that allow us for the so-called crystal mapping, serial ED, and automation, where you don't need to move your beam, but you're moving your motors. At the present time, one of our customers has just received the latest electron diffractometer, and I just see that I didn't optimize this, because right now the sphere of confusion that they have, it's around 200 nanometers on that device. So here you have some videos of the goniometer and the inside of the machine, where I'm showing you the space. So you can see here on this video on the right hand side the height. We can move up and down freely. Here on the middle video you can see how big could a multi-sample holder be in this case, because we have space all over. Also here on the left hand side you can see the full rotation. So because of that, and compared to other systems, clearly we can adapt. We can design anything that fits here to hold multi-grids and even to hold multi-sample changer. And this is the holy grail of not only automation but high throughput. Now let me show you how precise our system is on a rotation. This is STEM mode, so we have a particle which is approximately, I would say, 500 nanometers in length here. And you see that at the different angles, going from -60 all the way to 60 in this case, the particle remains always center. This is because our system has been optimized for that. So when we collect the diffraction and we do the continuous rotation, basically the particle will remain in the center for the rest of the time. We have the so-called Octagon chamber, which has 8 ports. It's very spacious and has a lot of space for adapting new technologies or other technologies that you might be able to use. It's flexible. Its flexible designs allows us to customize new things there. Of course, it has the cryo capability condition, which is integrated now in our system. And then once we have produced beam, we heat our sample, diffraction is produced. Diffraction travels through the drift tube. And one important feature that our device has, which you cannot find in any other microscope, is the absence of lenses or condensers. Now, because we don't have lenses on condensers, we don't have any distortion that affects our diffraction peaks. And therefore, also, we don't need to be calibrated constantly our detector distance. So once the distance has been calibrated at the first time, the distance remains constant for the rest of the time. So because of that, and because we have better diffraction peaks. At the end of the day, what we are getting is very accurate or more accurate cells compared to any other device. Now, indeed, there's a study from the electron diffraction community, the non-ED, who have taken this into consideration and have done a round-robin study. Now, let me show you the results. They should be coming soon, or probably they are being published at the time we speak. They have tested different microscopes in the different facilities that can produce electron diffraction. And you see there the device that was tested and the method that was used for obtaining a structure. Our device was also part of the test. And at the end of the day, indeed, our device shows better results than average of all those devices that have been used there in this round robin. So our raw data can be used directly by anyone without knowledge on aberrations, corrections. There are no corrections or aberrations needed that we need to take into account because we don't have lenses there. Our raw data is not manipulated or changed for any processing purposes, and this is very important for pharmaceutical industry. Our raw data, as it comes from the detector, can be passed to the industry, and they can use it directly for their purposes of structural elucidation or other purposes. And our unit cell determination is easier and accurate compared to other devices. So now let's talk about automation using particle recognition. Here on the right-hand side, you have a video where you see that some meshes have been identified and have been numbered. We can do it also semi-automatically, so we can choose if we want to measure one of those or all of them or none of them. And once we have chosen our different meshes where the different particles are, the software will recognize again and number the particles which would be measured. We can always intervene if we want. For example, if one particle was not selected, we can select it, or we can deselect particles. Now, finding and identifying different meshes on the grid and find the different particles is already something that is working in our system. We are optimizing it also for AI to have a better recognition of the different particles. And indeed, our customer is getting already these capabilities that I'm showing you here. And then what we do is an automatic centering and automatic data collection, and at the end of the day, automatic processes of the data. Now, software is very important for automation, no doubt about it, but the high throughput is only achieved if you have the hardware capabilities. And this is where the ELDICO ED-1 device has a difference compared to all other systems available in the market. So now in this video, I'm showing you the process of centering, which this particle has been basically selected automatically. The machine would center at 0, then it would move to a certain degree, which we give, in this case, 30 degrees, and it would take another stem image. So like you do in X-ray crystallography, when you center your crystal, you put it at a certain position, you take a video of that, you try to put it in the center, you rotate to a certain position and center again. And with that, you align your crystal during this rotation. This is exactly what we do. So now you see here the crystal has been aligned. And now if we go on this small range on automation, then we can get diffraction on this particle from the range that we have given, as you can see here on the right-hand side. Now the process is very simple. Once you have collected your diffraction data, the software would move automatically to the next particle. That means we are moving our motors, we are not moving our beam. The particle is put again in this position. A stem image is taken at 0 degrees to center in the beam, in the focus part of the beam. It's moved again back to the angle where we want to start our diffraction, recenter again, and then the continuous rotation starts. So now you see it here in this particle. Indeed, this particle, which has a very dense area here, because probably it's an agglomeration of particles, the software will try to center at some corner where the density or thickness of this crystal is much, much lower. And then the process is repeated for all the particles that we have chosen or that we have told the software to select. So now let me show you a case of automation, and where automation indeed saves us time and money and resources. So the case study is a scientific collaboration with a pharma company. They have spray-dried samples, which is stored under certain conditions, stress conditions, 40 degrees Celsius and 75% room humidity. And they have seen that a new crystalline form has appeared. Now, of course, they want to know what this crystalline form is. So what we do, we disperse the powder on a TEM grid. We use our software in our electron diffractometer for measuring automatically in this experiment 104 particles from a rotation from minus 35 degrees to 0 degrees with 1 degree per measurement. And the total measurement time for each particle, as you can see, is around 105 minutes. Then we use dials, which is the software that we have integrated in our system to do all the process automatically. Now, after using collecting the data and using the software, we saw that the software identified 45 particles which were indexed, and we found a unit cell there. Now, these 44 particles were clustered in two major clusters. I'm not going to go into the details. At the end of the day, it's the same cluster. It's just a different representation here of the beta angle, but let's just take in case this one, the one that shows the more amount of particles, and let's try to work on that one. Of course, we can select each other one if we need it. So by doing that, now I can compare times of a manual operator with automation. And basically, when we're doing a manual measurement, we would require around 3 to 4 hours to collect certain amount of data sets that are usable for our structure solution purpose. Now, if I try to normalize that and I put it to 120 data sets, which was what I just did collected right now or show you right now, basically you can see the amount of time that has been saved. So in that sense, we're talking about already almost 2 full days of an FTE. Now, the processing the data also requires manual intervention, which takes time. But now with the automation, of course, here there's not much difference, but still there's a minor difference, which is helpful also for us. So at the end of the day, we can produce it manually, right? But it requires an operator. It requires a crystallographer, the knowledge of him being used for this. We can do the same with automation. And in fact, what we see right now, because we are collecting much data, is that we even improve on our statistics and we improve on our structural model. Now, let me show you this with exactly this case example of this particle. So now you can compare between the amount of data sets that the operator, the crystallographer, decided to use for this experiment, when in this case, the automation just takes everything out there, makes the best out of it. So you clearly see on the right-hand side, the comparison, and in bold, you see those fields where the automation has made an improvement in the statistics or in the data quality of this structure. And last but not least, if we refine the structure, a crystallographer, of course, is needed for this. The machine can do it, but for very, let's say, straightforward cases, here's where your input is needed as a crystallographer. Here's where your knowledge. So now you can save the time of being in front of a machine and collecting data and processing data by doing it automatic. And you can use your valuable time, your knowledge for this part of the process to get the better structure out of your data. Said that, let me conclude. The bottleneck for each ED experiment used to be instrumentation, but now that's not a problem because we have a dedicated device and a dedicated electron diffractometer. Our device, the ELDICO ED-1 Diffractometer, has been optimized in various things. So geometry, that means it fits anywhere. Beam optimization, which is stable, requires no calibration. It's optimal for organic molecules. Geometric optimization of our motors, so we have a small fear of confusion, precise and constant rotation. We can have multi-sample holders, which enables us to do high throughput. We have no optics after the sample, therefore we have better data quality. We don't need to do any manipulation on the raw data. We have accurate unit cell determination, and our raw data is comparable with single crystal compatible, with single crystal X-ray diffraction software. Last but not least, software optimization allows for automation, for particle recognition, centering and measuring, and data processing. Last but not least, a dedicated device like the ELDICO ED-1 Diffractometer opens the future of electron crystallography and electron diffraction, makes it possible for everyone to perform ED experiments, and makes it possible to do 24/7 experiments, even if you're not an experienced crystallographer. And with that, I want to thank you for your attention. This is the ELDICO ED-1 hardware and software are ready now for paving the future of automated ED. If you're interested, you can contact us. My name is there. You find me LinkedIn, our company. You find us on the web or also in the social media. Thank you very much for your attention. I hope you enjoyed this presentation.